Thank you, Johan, for a generous introduction and for the honor and privilege of being invited back here to Frankfurt for a second time. Of course, the first time you organized for a completely full room, but I wasn't competing with German football last time I was here, so shame on me. As Johan says, I work for a company called North Sails, and our business is performance sales for racing yachts. In this game, the strongest structure for the least possible weight is the name of the game and the most important aspect. So traditionally, to dig deep down in our business a little bit, traditionally sails are made from woven panels of fabric and they're sewn together. So while this is still very nice aesthetic, of course, even if not so high tech, but you can see these are panels cut off rolls of woven material, and the joins here are stitching. So stitching or sewing is the nuts and bolts in the textile business, so your shirt is no different. Sections of woven material cut out and fastened together mechanically with stitching or sewing machines. But today in our business, sail making looks like that. So not a sewing machine or very few pairs of scissors in sight. So sails are made in one piece with bespoke fiber placement on three-dimensional curved surfaces that are adjustable, using advanced robotics and software. So the process is mostly automated. And as a way to sort of start and give you an overview of the factory and the way the machinery operates, I'm going to show you a little video to start with. It has some pictures of the machines in motion, and also at the start of this video are some friends of mine trying to sail a 110-foot sailboat around the world in the shortest period of time ever done. So it's kind of a race against the clock around the world. And in this photograph, they're sailing through the Southern Ocean. And the noise you hear at the start of this video is solely of a large carbon fiber object moving through the ocean as fast as it can. And you'll see that sailing around the world is, in fact, no picnic. to step back from the noise and the high technology for a second and come back to sort of the creation story for this product and this methodology. So this method we have here at Build and Sails full size on articulating tools is 22 years old now. So it's, you know, you almost say it's a mature technology. And one of the things we discussed this afternoon, and one of the things that's always a topic whenever I talk to architects or aspiring architects, is how come it doesn't happen in our business, or when is it going to happen? So I'll just tell you about how it happened in our business. So this is, these are sewn together panels. So these are vertical panels instead of the horizontal panels that were in the first sailboat picture I sewn. But it's the same method of assembly. Things are sewn together. And so both textiles and sails are as old as mankind. This is a technology that's 4,000 or 5,000 years old. Textile, generally recognized to be older than pottery, and sailing is kind of the original mode of long distance travel by humans. So everything, this has been done in our business for thousands and thousands of years, even before it was a business, so to speak. And so two young Swiss guys in 1990 came up with the idea that they weren't going to do things that way anymore. So they were going to do things this way. They were going to take the raw materials that were used to make those panels, and they made a decision to do three things differently. They made a decision that they were going to take the orientated fiber, high-tech fibers, carbon fiber, or aramids, or Dyneema, and they were going to run it corner to corner. They decided they were going to do it on a three-dimensional mold, and they decided that mold was going to be adjustable. Just insane. So they decided to do three things at one time, all together, that had never been done before. So it's just crazy. I still can't believe it, but it's been remarkably successful, and I guess that's how the world becomes a better place. Some crazy people just decide they're going to do something, and they find the investment, and they make it happen. And it's as simple and as complicated a story as that, but even 22 years later, it's really, really amazing story that some kids just decided to do it. And so here's some early 3DL sails. 3DL stands for three-dimensional laminate, because we're truly making the structure in 3 dimensions. And 3 dimensions is important in our business because when the sails are up and flying or inflated on a sailboat, they're 3-dimensional shapes. And so it was a critical breakthrough to lay up all the materials in 3 dimensions, or effectively the same shape the sail was going to fly in. So some other interesting aspects, I think, are that in a modern performance sail, the fiber orientation is asymmetrical. So obviously in a woven material, you have symmetrical orientation of the fiber. Mostly 0 and 90, maybe some 45s in there, but the fiber spacing and orientation is symmetrical. But in a modern structure, it's an important feature that the fiber is asymmetrical and it's placed only where you need. So you can see in the corners of a sail, from where the loads are reacted, you have bigger density clusters of fiber, and where there's less load, you have a little bit less fiber. And even in the body of the sail, where there's very, very light loads, there's no fiber at all. So that's an important aspect of creating the lightest structure you can for any given application, because the main way to make something light is to take material out of it, to use less material to build it, obviously. And both lightness and fiber asymmetry, or economy of materials, is also good as far as cost is concerned, not only lightness. So a sail is created with bespoke fiber placement, fiber placed in the structure in anticipation of the loads and the variations in the stress field as the boat moves through the waves. We talked about this again a little bit this afternoon, but I think this is a critical component of any structure, be it a sail, a mast, a boat, or an airplane wing. It's going to be made as light as it possibly can. You know, it's going to be made with orientated materials. So you have to understand about material orientation as an integral part of the structure, and the way these structures are created or processed is therefore integral to the design, you know. And just to kind of use an example, you often hear statements, or you might read things like carbon fiber is 50 times stronger than steel for its weight. And I don't even know if that's the right number, but you hear things like that. And so one of the reasons that's true or that's possible is that materials like steel, glass, and concrete are what we call isotropic. So they have the same properties in every direction. So, you know, if you pull on them in the zero axis, they have the same properties as if you pull on them in the zero or you pull on them in the z direction, all right? And you know, having equal properties in all directions like that ends up with a material that's quite dense or quite heavy. So one of the keys to high-tech fibers and light materials that are very strong is that they're actually only strong in one orientation, which, you know, is never mentioned when you're talking about it being 50 times stronger than steel. It's only 50 times stronger when you pull it in the direction of the molecular structure. In any other direction, it has from greatly reduced to zero. So if you pull on a carbon fiber along the orientation of molecular structure, it's really hard to break it. If you pull it 90 degrees to that, a raw fiber, you know, not one that's embedded in a matrix, it just instantly comes apart. It has zero. So asymmetry of material orientation, asymmetry and material orientation are critical in making light structure. So there's a little bit more sophisticated structure, a little bit further down in the maturity of the product. So that's an all carbon fiber sail. And again, you can see enormous density clusters in the corners, less and less material as the out in the body of the sail where the loads are a lot less. That's a photograph of a boat that's about 150 feet long, weighs 240 tons. In the corner here, it's the highest loaded part of the sail. The stack of carbon fiber and aramid is about 30 millimeters thick. Out here in the body of the sail, it's maybe 2 millimeters thick. Right? So that is kind of another feature of fiber orientation, but a density cluster there can handle maybe 20,000 pounds of load. And then it fans out into almost nothing in the center of the sail. So a very efficient structure as far as tensile loading is concerned. And sails are pretty much wholly tensile structures. Here's a look at, again, the three-dimensional laminate being made in the factory. So the silver surface is an adjustable and articulating mold, and it's just a metallized nylon cover on the mold. And you can see the sail being built full size there, and the fibers being laid down on what we call a mylar film, which is a polyester film with a thin coating of resin on top. So you can see the fiber runs corner to corner, uninterrupted, laid down in 3 dimensions. So when the sail is, when we talk about sail design, we're talking about 3 separate things. So one is the geometry, the exterior geometry of the sail, which is in 2 dimensions. One is the aerodynamics, or the flying shape of the sail, and the third is the sail structure. So when a sail is designed out in the field, it's designed more or less locally where the client resides, and he keeps his boat. And we're basically talking about the aerodynamics first of all. And so the aerodynamics of the sail are determined for the wind speed it's going to be used in the sea state. So you have kind of different curvatures and aerodynamic shapes for different wind speeds and sea state. So anytime you're talking about large boats, any individual sail is unique pretty much in terms of geometry, aerodynamics, and its structure. So what we're about in our factory is a customized item for any particular application for any particular customer at any particular time. We rarely build 2 things the same. The process is always the same, but the individual item is completely customized. It's a form of mass customization. So here we're just looking at a sail design, or the aerodynamics, and the geometry is sent to the factory electronically, and then we've got 9 of these adjustable molds in the building, and here one of our technicians is determining which mold the aerodynamics of the sail and the geometry will fit on best. So he's positioning on the wireframe rendering of the mold. That's a look at the mold technology that you saw in the video a little bit. So again, adjustable surface here with a nylon covering on it, metallized nylon covering. Pultruded fiberglass running in the 0 and 90 axis underneath the mold. None of that fiberglass is actually fixed to the surface of the mold, because as the mold adjusts into an aerodynamic shape, it has to grow or it has to shrink. So those rods aren't fixed, and you can see the lifter armatures here that are driven up and down by a vertical worm screw that is attached to 2 pneumatic actuators. So 2 pulses of each actuator drives the vertical worm screw around, which lifts the pantograph lifters up and down in the z-axis in vertical space. One more little video here, look at a mold adjustment. So this is a time-elapsed version of a mold adjustment. It's an overhead gantry with all the fiber placement tools and a laser spotter to check the mold adjustment. So that process there takes about 5 or 8 minutes to adjust the mold from flat to inflated into the aerodynamic shape. And it's a push button operation. Underneath this largest mold there's about 350 lifting mechanisms or so. Let's look at the leading edge and the amount of curvature that is required in the leading edge of the sail. And just kind of look there at the fiber architecture and the overall look at the fabrication strategy of the factory. So this is basically an automated process here, and the operator follows along in a hang gliding bag and is effectively quality control. They're not operating the system, although they can stop the system if there's a problem. So look at it. Better look at the fiber placement head. So there's spools of fiber up here out of the picture, drop down through the head. You can see there's a resin reservoir there, and there's a resin bath, 20 mil resin bath, right in front of the tire there. The fiber's pulled through the resin bath and wetted out with adhesive just before it's laid down on the surface of the mold. And just kind of another look at that process. Operator holding on for dear life. And again, fiber placement head, reservoir in and out, reservoir bath, and a segmented tire there. So that tire is in 3 sections, so when you go around a tight radius, the fiber's on the inside and the fiber's on the outside of the radius. You know, they're not in either tension or compression. They're laid down more or less in equal tension. And again, as the fiber fans out from the corners with the highest loaded part of the sails. It's the body of the sail. And after the fiber architecture is laid down on the film, we pull 2 more films over the top. This is what you call the mid film. It's got a scrim on it that provides a little bit of tear strength, so a little bit of off-axis load carrying ability in the direction that the fiber doesn't have any strength in. So in the direction of non-orientated direction of the sail. And a look at look again. So once the fiber architecture is loaded, then they're building a vacuum bag around the sail. So the feature of composites, or certainly these type of pre-preg composites, is that the sail is cooked or heated, and that's done under pressure. And at this sort of scale, you do that in a vacuum bag. Under smaller scale, you might do it in a cylinder called an autoclave, but in large scale, you use vacuum pressure. You suck the air out between the sail. It sucks out any moisture or any solvents or volatiles. At the same time, the films will consolidate all the materials under pressure, and you pass heat over the surface. There's a vacuum pressure pulled on that sail, and then while it's under pressure and the materials are being consolidated, you pass heat over the surface. It flows the adhesive commingles and bonds the fibers to the film. So So it's important that it's heated at the same time it's under pressure. And I was looking at the operator. This is what we call an infrared heating system. So there's infrared energy fired into the surface of the laminate. It excites the molecules in the adhesive and heats them up. The operator there has got a little infrared temperature gauge, so they can kind of check that the surface of the laminate is appropriate to make the adhesive flow that's encasing the fibers. This is just a kind of a fun look at the scale these things have gotten to now. Our boat is 66 meters long. The top of the mast is about 78 meters off the water. This sail is glued and sewn together in a traditional manner, but the dark sail there, which we call the main sail, was built on our molds. That's 1,080 square meters, that sail. It's actually bigger than the mold, so it was made in a couple sections and glued together. That sail is about 3,000 square meters. Let's just kind of look at the scale. You see the size of the people there, and the scale of the boat and the sails. They're pavilions almost in the scale. And there's a look at the sail being folded up, and we rented a separate shed outside of where all the molds are, so we could fold the sail up and do the quality control. So I think we had 33 people in the morning folding up that 1,000 square meter sail that weighed 1,600 kilograms. So it's the lightest thing you can make for a boat that size, but still substantial as far as mass goes. So that's our original technology that as I was saying, was 22 years old, 3DL for three-dimensional laminate. And in the last few years, we, along with a couple of different Swiss guys, why all the technology in our industry is originating in Switzerland, I have no idea, but it has been. So we came up with a new technology where instead of laying yarn tows or fiber tows on films in a load path or structural anisotropic structural orientation, we're going to make sails completely out of pre-impregnated fiber tape. So there would no longer be any film or any substrate. So here's an example of a 3DL sail in the back, and you can see the sort of the classic fiber architecture in the orientated direction. This sail is made out of pre-impregnated tape, just like any other race car, airplane wing, and it's fiber and resin only. There's no longer any film or any substrate there. And to take a step back and talk about what we call unidirectional or pre-preg or orientated tape, that's a photograph of a single aramid or Kevlar yarn taken underneath a microscope. So the characteristic of what you think about as an individual yarn or a fiber tow is that in fact it's made up of a lot of different filaments. So in this case, there's 3,000 filaments in this aramid fiber. So that's one individual filament. It's about 12 microns, kind of the size of a human hair. The interesting thing about this is that in terms of the material's property known as modulus or stretch resistance, as opposed to strength, so those are different properties. Resistance to breakage is strength, resistance to stretch is modulus. This individual filament is about 15% better than that bundle. So for us, or for those in performance sport, when the whole goal is to make something as light as possible and as stiff as possible, this 15% is potentially a revelation here. So to use an existing material and be able to get 15% more properties, mechanical properties out of it, or stretch resistance, is quite a big deal, and was the goal of spreading this out into a tape. So those individual filaments here are taken out of the bundle and laid side by side in these super thin tapes. So one of those tapes is equivalent to maybe 12 of those yarns, and all the filaments are laid side by side embedded in resin. And so in that configuration, you've got the same material that your competitors are using, but you've improved the way the material is configured by breaking it down and reassembling it in the manner you desire, and it's 15% better material properties. So the implication of that is the sail can be 15% lighter or 15% less stretchy. And this is, in the composites world, this is known as a pre-preg tape for pre-impregnation. So the filaments are pre-impregnated with resin. So the sort of traditional GRP or glass reinforced fiber composite that people think about, where everything is goopy and soaked with resin, is eliminated in this process because, again, it's a high modulus fiber, in this case with a lot of strength as well. So fiber comes in spools or bobbins like this. So we're pulling the fiber off the bobbin into this pre-impregnation head over here. You can see the yarns or tows running into one side of the head. Here they're coming out the other side of the head, and they're starting to spread out here. So it's a yarn or a bundle of filaments up here, and you can see it's starting to flatten out into the individual filaments. And here it goes into the resin bath, and this is the yellow stuff here is just resin. And you can see they're spreading out and are almost in tape format now as they go into the resin, and the viscosity of the resin finishes the spread there out of sight. And we make this 600 millimeters wide. So here's a roll of thin Dyneema tape, about 30 grams per square meter. And again, the brown is just the paper backer that the resin and the Dyneema are laid onto, so we can roll it up or pull it off the roll. The material is then slit down to different widths for creating the structure. And this particular one is an example of a pre-impregnated tape that's both Dyneema and carbon fiber. So the white stuff there is the Dyneema, and the black is the carbon fiber. And in our business, many times you're going to combine different fibers to get a different characteristic in the sail. So for instance, carbon fiber is very stiff or very high modulus, but it's also very brittle material, particularly if you need to flex it or fold it as you do in a sail membrane, where Dyneema is not very brittle and it has a lot of strength. So combining the two is advantageous for the flexible membrane industry that we're in. Going back to an all Dyneema tape here, so this is slid off that 600-meter roll and plugged into our fiber placement head. ATL stands for automated tape laying, was the industry phrase for automatic fiber placement, automated fiber placement. And there's a look at one of the heads, in this case laying down carbon fiber tapes. So in this stage here, you can see it's not on the curved mold. So we're laying, that will come later, we're laying down what we call a preform or a complex here in 2 dimensions with this tape laying head. But it's the same philosophy as the yarn tow head that you saw laying down materials on the mold. So you're orientating materials according to a structural design. You're building up density in different parts of the structure. And you can kind of see here there's some embedded reinforcements in the structure of this sail for places where in particular hardware is going to attach, and the loading in the sail will be influenced by the hardware attachments, not just the structural loading as the boat's powering through the waves. And there's a couple of different sections being plotted out on those tables. And there's a look at a sail structure with the sail made out of these pre-impregnated unidirectional tapes. So you'll plot out sections of tapes, all different orientations for different layers of the sail. Will be handling different load paths. Some orientations for modulus or stretch resistance, other orientations for strength and for flex. And different parts of the sail will have different orientations, different density clusters, and potentially even different materials. Then those complexes or preforms are stacked together inside a vacuum bag. And then we come back to the 3-dimensional mold technology. So we'll stack those preforms or complexes inside a vacuum bag on the three-dimensional mold. So there's the first one going in the mold, and succeeding sections will be joined. Pull the vacuum to consolidate all the materials, just like in the early photograph, earlier pictures, and heat it up again with the infrared lamp to consolidate the membrane. So in this case now we've gone really completely out of the textiles business, where a sail is just fiber and resin, just the way an airplane wing is, or a boat hull, or a racing car, or any other structure. The difference is it's flexible, and flexibility comes mostly from the resin system we use. So we use a very high elongation polyester resin system in these sort of flexible membranes. So we've then taken this technology, which we call 3DI or thin ply pre-preg technology, moved it outside of our flexible membrane or sail technology, and started to bring it into sort of traditional rigid composites manufacturing that are epoxy matrix based, and again, not flexible structures but rigid structures. And one of the things we bring to aerospace or motorsport is the fact that we create a thinner tape with our process than anyone else does because of the requirements for sails. So here's a extremely thin 16 gram per square meter carbon fiber tape. And here's a look at some large carbon fiber structures. So you remember that boat I was talking about that was 66 meter. Here's the top of the mast on a 58 meter boat. So that's an all carbon fiber mast weighing many tons, made completely out of this carbon fiber pre-impregnated tape. So you get an idea for scale there. And most carbon fiber composites today outside of the aerospace industry, like Boeing and Airbus, where they have massive investment in machinery and technology, and they do things in an automated manner. But everywhere else in the composites business, whether it's motorsport and Formula One or very large masts, composite materials are still pretty much laid up by hand. So there's a few of our guys in New Zealand laying up a huge spar for a 58 meter boat, one pre-impregnated strip at a time, leaning into the molds. So one of the things we intend to bring this business is sort of our fabrication systems and our automation here. So we're going to also plot preforms for rigid composite structures with these epoxy matrix prepregs, made the same way as our pre-preg tapes were for our sails, plotted out with more or less the same machinery, but for the rigid composites business. So there's a preform being plotted out for a mast for a 30 meter boat. Wrong button. And these are what's called the boom. On a sailboat you have carbon fiber structures that the sails hang off of. One's called the mast, one calls the boom. So there's some pre-impregnated complexes being plotted out for the booms. And here's a complex being laid inside a female mold here to build a mast. So more or less the same process we use to build the sails, we're now bringing that to rigid composite structures as well. There's a photograph of some mast, carbon fiber mast here, and our 3DI or pre-preg tape sails. So this is being a rigid structure, this being a soft membrane sail-like structure, so a textile in feel and flexibility, but made with exactly the same process, the main difference being the resin system employed to embed the fibers and hold the structure together. And quick look, this is a round-the-world solar-powered plane project being done in Switzerland. This is a 60-meter wingspan plane that flew last summer. Right now we're involved in building the actual plane for this adventure. It's an 80-meter wingspan, going to be built using these thin pre-preg materials. The complete weight of this 80-meter plane with 4 electric engines will be 2,000 kilograms. And some of our materials are now being used in motorsport. On the Red Bull team, the engine covers back here on the body fairings are made using our materials in this same system. There's just a rendering of the different sections of pre-preg that will be placed on the mold for that engine cover and plotted out using the same system. This is just a study for trying to use the same process and this level of automation to do things on a larger scale. So that's a study for using the same system to build the hull of a 52-foot yacht. And this is like the spine, the backbone of the spine of the yacht, which the structure would all be, again, embedded in and placed automatically with our fiber placement system. Just quickly, I think Greg will probably talk a little bit about this. Greg and I have worked together on a few projects. This was the first one we did using our 3DL or fiber toe placement system orientated laminates, and we made these quasi sails for the Swarovski company, and we bedded 1.1 or 1.2 million crystals in the surface of these 4 sails here. Swarovski crystals for Swarovski stand at Art Design Miami a few years ago. Just another look at that. Here's another project at Greg's where he used our pre-impregnated tape sail technology to make a few very light chairs. I won't talk too much about this, but again, this is a molded, I guess I call it a molded, I want to say molded textile, but that's not right. It's a molded composite that looks rigid and has both tensile and compressive properties, vacuum bagged and heated, but also super flexible and super light. So those can be folded or rolled, and they weighed less than a pound, and Greg's had his whole family in them, so he can carry roughly 1,000 times its weight, that structure. Look at it. And quickly, Johan mentioned I was involved with the Southern California Institute of Architecture, involved in teaching a seminar there this year, and this is just an interesting project I'll throw out there for a pavilion that ended up growing from a student project into a real-life submittal for a temporary pavilion that is going to be financed by the Museum of Contemporary Art in Los Angeles. They're going to finance 4 or 5 temporary pavilions by some young architects in LA. And this is a proposal for that pavilion. And one intentional aspect of this is that, again, these would be our unidirectional pre-preg tapes. And by changing the density and the type of materials in the surface walls of this pavilion, it will vary the opacity. So obviously these might be carbon fiber tape structures here, and out here we use that Dyneema material that's almost clear. So this will all be surface and fiber structure, but some of it will be almost window-like because it will be very, very clear and very, very thin, and other areas will be more structural and more opaque. And just a picture of these plotting heads in a short video, because I think it gives another idea of the potential scale you could imagine things being done on in the future. Six plotters and fiber placement heads all operating at the same time. If we build in different sails or sections of the same sail structure. The end. Thank you.
Some questions? With this current system, you have a set structure with one resident variable. The compressive loss with the different computing system where on one table you use both tapes because there's a structure that has both situations.
Yeah, okay, good question. In fact, the tape head is somewhat modified to use a different resin systems. So the epoxy resin system does have a different tape head. It's not wildly different, but it is a little different because the sort of viscosity and attacks of the resin are completely different. And also, when we're building mass or carbon fiber structure, we want a tape head that has the ability to lay down not only very thin materials, but like that 58-meter mast has a lot of material in it. So you wouldn't try to build that using 16 gram per square meter material. You'd want to sort of use 300s. So that requires a head that has kind of a depth of field to handle a large variety of weights, whereas the sail making head only needs to handle really the thinnest materials we can handle. However, I will also say that for the sails, there's actually two resin systems, although they're both polyesters. The interior of the sail is built in a really high elongation system that doesn't really cure hard 100%. The surface tapes are built with a much harder resin system that has some abrasion resistance and cures much, much harder. Anybody else?
Well, actually, you have a wonderful term there. You speak about, you mentioned design space. I was wondering if you just explain to us very briefly what that entails in some of these more complex projects. If I remember correctly, one time you even said that ideally these sails should be designed really in conjunction with the design of the hull, not simply as something that was then added to after completion of the boat.
Yes. In fact, the main reason we own a mast making company, so to make the carbon fiber spars, is because we really want to design those at the same time as the sails are designed because it's much more efficient. The carbon fiber mast business is nowhere near as good a business as the sail making side, but aerodynamically you have a much more sophisticated package if you design them both at the same time, and particularly because we're now supplying the base materials for both. The sail designers and the mast makers can work together on one project and make a much more sophisticated aerodynamic package. So, to some degree, the same is true on the boat, although boat building's a business of a completely different scale than master sail making. But yeah, at the highest level of the sport, which is like the America's Cup yacht race and there's a current race around the world called the Volvo Ocean Race. At that level of sport, the mast and the sails and the hull are designed by a team of people that all work together and more or less design the whole package to work together.
And then you then integrate your know-how and your design expertise with someone who's managing the whole project, or how does that work?
Yeah, well, On a high-level project like that, there'd be a group of people that were working together from the start. There'd be the yacht designer, who does the shape of the boat. There'd be a structural engineer for the boat. There'll be a mast designer, who is in fact a structural engineer for the mast, and there would be a sail designer as well, who is in charge of the sail aerodynamics, and they would all work together. And sometimes they all would even work off our software programs for a large percentage of that. So we have software programs that can do most of that work. Not always, though.
And each of these then represent a winger and material expertise, or is that an additional material expertise? Is that an additional layer of?
I would say the material expertise is kind of outside that working box, because those people would work off data, material performance data, the same way a structural engineer for a building would do. So there'd be a given set of data for particular materials that we would have to have generated, obviously, but our sail designers would have that material that was generated by our chemists and our materials specialists, but they wouldn't be part of that design package. They would produce information that would be used by those engineers and designers. We don't, there are no competitors left in our business with the scale to do this. Yeah, so they've, the success of this project and this process has sort of catapulted us from being the major player in the business to being kind of like the Microsoft in our business. You know, we're almost 50% of the industry now, and you know, the sailing industry, not only sail making, but the sail industry is quite small, so there's now a barrier to investment in our business to really play at this level.